In this section, we're going to look at how to test for differences between means from two separate groups of subjects. A later section describes how to test for differences between the means of two conditions in designs where only one group of subjects is used and each subject is tested in each condition. It is much more common for a researcher to be interested in the difference between means than in the specific values of the means themselves. We'll take as an example the data from the animal research case study. In this experiment, students rated whether they thought animal research is wrong on a 7-point scale. The sample sizes, means, and variances are shown separately for males and females. As you can see, the females rated animal research as more wrong than did the males. This sample difference between the female mean of 5.35 and the male mean of 3.88 is 1.47. However, the gender difference in this particular sample is not very important. What is important is the difference in the population. The difference in sample means is used to estimate the difference in population means. In order to test whether there is a difference between populations, we are going to make three assumptions. 1. The two populations have the same variance. This assumption is called the assumption of homogeneity of variance. 2. The populations are normally distributed. And 3. Each value is sampled independently from each other value. If a subject provides two scores, then the values are not independent. The analysis of data with two scores per subject is shown in the section on the correlated t-test later in this chapter. The consequences of violating the former two assumptions are investigated in the simulation in the section on robustness. For now, it is enough to say that small to moderate violations of the first two assumptions do not make much difference. However, it is important not to violate assumption 3. In the section on testing a single mean, we saw this general formula for significance testing. The t-value equals the statistic minus the hypothesized value divided by the estimated standard error of the statistic. In this case, our statistic is the difference between sample means and our hypothesized value is 0. The hypothesized value is the null hypothesis that there is no difference between the two populations or that the difference between population means is 0. We will continue to use data from the animal research case study and will compute a significance test on the difference between the mean score of the males and the mean score of the females. For this calculation, we will make the three assumptions specified previously. The first step is to compute the statistic, which is simply the difference between means. The mean of the females minus the mean of the males equals 1.47. Since the hypothesized value is 0, we do not need to subtract it from the statistic. The next step is to compute the estimate of the standard error of the statistic. The statistic is the difference between means, so the estimated standard error of the statistic is indicated by S sub m1 minus m2. The standard error of the difference in means in the population is shown here. Remember that we are assuming the variances are equal, so the variance of the females is assumed to be equal to the variance of the males. Normally, we estimate the variance of the populations using the variance of the sample. But we just said that we are assuming the variances of the female and male populations are the same. However, the sample values are not the same, so which sample variance do we use to estimate the population variance? We estimate the variance of the two populations by averaging our two sample variances. Thus, our estimate of variance is computed using this formula. MSE is our estimate of the variance of the populations. In this example, MSE equals 2.864. The upper formula is the formula for the standard error of the difference. The lower formula is the formula for the estimated standard error of the difference. Notice the difference on the left side of the formulas. The population formula uses sigma, whereas the estimate uses S. Notice also that MSE, which is the average of the sample variances, is used in the formula for the estimate. Both groups have the same number of scores, 17, so our n is 17. Now we can calculate our estimated standard error of the difference, which equals 0.5805. So now we have all the information we need to calculate t. We have the difference between the means of our two groups, which is 1.470. We also know the estimated standard error of the difference between the means, which is 0.5805. Therefore, t equals 1.470 divided by 0.5805, which equals 2.533. Finally, we compute the probability of getting a t as large or larger than 2.53, or as small or smaller than negative 2.53. To do this, we need to know the degrees of freedom. The degrees of freedom is the number of independent estimates of variance on which MSE is based. This is equal to n1 minus 1 plus n2 minus 1, where n1 is the sample size for the first group and n2 is the sample size of the second group. Therefore, the degrees of freedom is 16 plus 16, which equals 32. Once we have the degrees of freedom, we can use the t-distribution calculator to find the probability. The two-tailed test is used when the null hypothesis can be rejected, regardless of the direction of the effect. As shown here, the probability of a t less than negative 2.533 or greater than 2.533 is 0.0164. The results of a one-tailed test are shown here. As you can see, the probability value of 0.0082 is half the value for the two-tailed test. So back to our example. Remember that the difference between the mean score for the males and the mean score for the females was 1.47. Since the two-tailed p-value is very low, we reject the null hypothesis that there is no difference between males and females and conclude that the mean for females is higher than the mean for males. Most computer programs that compute t-tests require that your data be in a specific form. Consider the data in the table here. There are two groups, each with 3 observations. To format these data for a computer program, you normally have to use 2 variables. The first specifies the group the subject is in, and the second is the score itself. The table on the right shows the data reformatted into 2 variables. Notice that there are 6 rows now instead of 3. This is because there is a row for each observation with the group assignment and score for each. We have just reviewed an example of testing the difference between 2 means where the 2 sample sizes were equal. Of course, sample sizes are not always the same. The calculations for unequal sample sizes are described in the text of the standard mode for this section.